Hello and welcome back to Extreme Academy Live. This is where you can come to advance your knowledge, advance your skills and advance your future. Thanks for advancing with us. This is session 2. Thanks for joining on session 1. Last week we got off to a great start. Just as a quick reminder, you can interact with the Extreme team. You can send us a message in the chat. I'll be moderating the chat through today's session. Or if you've got a longer question, it's a technical question, then go to our Q&A app. You'll see the QR code over my shoulder or the URL on the screen somewhere. And that's where you can go and you can ask a question, you can get into a conversation with one of the Extreme experts or somebody else from the class. And there's lots of people on here that have got a lot of knowledge about this subject and they'll be helping out and answering your questions. And to all of you, thanks for joining and sharing your knowledge during this course. So Isaac, you out there? How's your week been and what have you got on the menu this week?
Yeah. Hi, Rowan. Hi, everyone. So how's my week been? Oh, the week's been fantastic, right? We did get off to a really good start. Exciting. Lots of people interested in wireless, and I'm not surprised. It's one of these kind of like mystery technologies, and we're gonna unravel it. We're gonna remove the complexity out of it. We're gonna make it really easy. I had a great week preparing, doing rehearsals. You know, I go through the content, through the slides, and I rehearse them over and over again to try and get the delivery right. So it was a good week of working through the stuff and getting ready for today's broadcast. So yeah, very good. On the menu, like I said, last week was more of a recap of, well, not a recap, but a big overview, a big picture view of wireless and how corporates and organizations kind of look at wireless and the technologies involved. Today, we're going to start getting into the actual radio, and we're going to start talking about that. Very cool. We're going to start with a little recap, and then we're going to jump in one of the couple of new things that I've introduced, but you're going to see me driving around Cambridge, new elements, interactive elements, things that have been recorded before. So that's going to be pretty cool. You'll need to stay tuned and watch this whole thing through. Going to be very cool today for sure.
That sounds great, Isaac. Looking forward to that. So today we're getting into more of the science, more of the technical topics. So, you know, make sure everybody you ask questions, you know, reach out to the engineers through the Q&A app. Now, before we get started, Isaac, let's just talk about a few things from last week. So there was a bit of fun last week. You had some fun with the audience in a number of ways. Let's just talk about the April Fool's piece to start off with. How did that go down? How are you feeling this week?
Well, I'm feeling good, thank you. It's like, I read what they gave to me to read, right? It's like, it's not my fault.
That was great. That was great fun. Was just in case anybody didn't realise it was an April Fool, then you know, optimizing radio waves for language was a little joke. It was definitely an April Fool, and hopefully you didn't write that down too seriously in your notes. So great to have a bit of fun, Isaac. And there's also something else new last week that we're going to continue, which was we're going to encourage everybody to stand up and just move around for 60 seconds, not be sitting in their seat. How do you how do you feel about that, Isaac? It looked like you were starting some exercise classes as well.
Well, you know, it's more for the older people, you know, not young people like you and I. It's more for the older people who, you know, if they don't get up and stretch, you know, then their body starts to creak when they get up. So the idea was just to get up and stretch 1 minute. It's not it's not like a halftime 10-minute break. Just get up and stretch. And so, then we thought, yeah, let's make it funny. Let's make it humorous, because that's how, you know, we do things here at the Academy. We're not like the other boring training. We want you to be involved. We want you to laugh. We want you to do the training, but we want you to enjoy it and smile with us. So if you don't stretch, then at least get up off your chair and have a smile at what's going on the screen. You know, at least smile. That will make us cool.
That's fantastic, Isaac. So more of that to come. We're gonna have some fun with that as we go forward in the weeks ahead. Okay, let's get going. I'm gonna jump on the panel now and the chat window. So I'll say hi to you over there. So Isaac, I'm gonna leave it to you. Take it away and let's start week 2.
Thank you. Let's go. Okay, so here we go. On to lesson number 2. This initial lesson, it's quite a short lesson, and this is about a recap of what we did in course 1. So course 1, for those of you who've watched, know that we addressed Wi-Fi, the concept of Wi-Fi, and specifically terms. We spoke about the number of different terms, the terminology that's involved in Wi-Fi. And so this is going to be a recap. If you haven't watched it, I suggest that you go watch it. I think it's in episode 3 or 4, where I cover a little bit of wireless. Now, in this module that I'm going to do now is just a recap of that. So a lot of the principles and the stuff that I'm going to talk about here, just think of it as a quick recap, because we are going to deal with most of these topics in specific lessons as we go along. This course on wireless networks. So I have a tablet in front of me, a Wacom tablet. So occasionally you'll see me, if I need to draw something on the screen, you'll see me looking down so that I can draw and make it easy to illustrate what I'm trying to say. And then to my left, I have a keyboard, so you'll occasionally see me switching to laser, pointer on screen, or a pen color, etc., etc. So that's what's going on. By the way, just so you know, as a matter of interest, this whole thing, this whole course has been filmed entirely on an iPhone, right? On an iPhone. So I just have an iPhone in front of me, and it's really pretty phenomenal that you can do this type of stuff in 4K and broadcast out, you know, from a mobile phone, right? It's like I said in course 1, it's not really a mobile phone, it's more like a mobile computer, right? Okay, so let's start by talking about the terminology that you hear around today when people talk about Wi-Fi. It was very common within the last few years to talk about all the different standards of Wi-Fi. And the IEEE, the body that covers all of these standards and the engineering, they have numbers that they use for all of the types of standards. And so for wireless, it's 802.11, right? 802.11. And within that, there's multiple different amendments for the different revisions of Wi-Fi technology. Now, it's not the easiest of terms, right? 802.11, and then is it, did you say A, B, was it F, G, H, K? For the IEEE and the engineers, this is perfectly clear for them, because, you know, that's how these guys do these things. But for the rest of us, we like really simple stuff, really easy ways. And so the IEEE or the wireless authorities came up with this, which they said, well, why don't we just call it, you know, a generation number? So Wi-Fi 4, Wi-Fi 5, Wi-Fi 6. And I think that kind of makes sense to me, right? I know that we talk about Wi-Fi 6. So Wi-Fi 6 capable devices. Yeah, that makes sense, right? It's Wi-Fi 6, yeah. Now, I know that even now they're saying like Wi-Fi 6E, but it's still Wi-Fi 6, which people can relate to and associate to, and it's very easy to understand. The engineers, the guys from the IEEE, they refer to it as 802.11ax, right? AX. Now, these are all just revision numbers, right? It starts with, you know, A, B, C, D, E, and once they ran out of letters, then it's like, oh, okay, let's go and add new letters onto these things. So the latest standard is called 802.11ax, known as Wi-Fi 6. Within these standards, within these different generations of Wi-Fi, initially when they were released, initially when engineers did these things and the marketing companies started talking about Wi-Fi, they would use the speed, you know, as the selling point. Upgrade your latest, you know, access point or Wi-Fi network to to 802.11, G, whatever, because it can now offer this particular speed, etc., etc. And nowadays, we still talk about speed, right? If you ask people about, what's the speed of Wi-Fi today, they'll say, oh, well, compared to previous, it's much faster, it's much all of this. But if you really open up and you look inside the hood, if you look under the bonnet and you go and see what is happening, you'll realize that speed is certainly one of those things. But it's not so much only about speed anymore. If you think about an Intel processor, right? Intel processor, there was a time where everybody was just releasing, speeds that, this is a 2.4 gigahertz and this is a 2.5 and this is a 2.6, and everybody was concerned about speed. That's how you sold these processors or these computers. It's about speed. And then when those chips were getting so hot and they were frying right through the computer, started thinking, ooh, maybe there's something else that we could do. And they started using multi-core and all sorts of things. So today, you still hear people talk about, the processor, the speed in gigahertz of a processor or whatever. But nowadays, there are other things that matter as well. And so for Wi-Fi, it's the same thing. Speed is, of course, it's important, right? You want to have a fast connection to the internet. But when you can, within that amendment, make things a lot more efficient, when you can push more data down the same bandwidth, down the same highway, when you can pack more cars onto a highway and get them traveling all in unison and synchronized, then it's not necessarily that the speed is increased, but the efficiency of the medium has increased. And so these latest revisions to Wi-Fi, they have been able to do that. They've been able to take this kind of inefficient technology and start looking at the little things that improve efficiency a lot. But having said that, speed is still a thing. So let's look at this. 1999, generation 199, that's a long time ago. 802.11b, right? This is the standard that I remember. My first installation, when I ran my own business in South Africa, my first installation of Wi-Fi was with this 11 megabit per second, right? To one access point, I think it was. That's what I set up, and I was so proud. Everybody was like, wow, this thing really works, right? As the generations evolved, as the technology evolved, as the demand for wireless got more and more development, more effort, more engineering was put into this. And so you'll see that we went from B standard to A, right? Then G, N, AC, and AX. Those are the kind of revisions and that we've gone through, the generational revisions. And again, let's look at the radio frequency band. I know we haven't spoken yet really about radio. We're still going to be talking about that and the different bands. We will cover that in detail. But this, remember, is a revision. Radio bands have generally been two major ones: 2.4 gigahertz band spectrum and the 5 gigahertz spectrum. So 802.11b was only 2.4 gigahertz. The A was only the 5. And then came along the G, which is like also 2.4, but the N was then able to talk on both of those, 2.4 or 5. When we came to AC again, only on the 5, and then on AX, we have better, right? Really improved, because we've got 2.4 gigahertz, we've got 5 gigahertz, and we have 6 gigahertz as well. Theoretically speaking, not practically, but theoretically speaking, AX is capable of 9.7 gigabit per second, data rate, physical data rate. Do we ever see that in practice? No, probably only ever see it in a lab, under extraordinary conditions. But if you compare that to what we saw in a lab in 1999, imagine 11 megabit per second as opposed to 9.6 gigabit per second. Where we go into next, absolutely incredible, right? Now, wireless access points. When in course 1 we were talking about different types of networks, one of them that we spoke about was the most common one. I mean, I think everybody watching this video would remember or recall, or in their conversation would have heard somebody talk about a LAN. Oh, I have a LAN at home. A LAN. What is a LAN? Well, it stands for local area network. A local area network. Local area, area, small, your house, office, etc., etc. So local area network. Now, in a local area network, generally speaking, all the components are connected using cables, using Ethernet cables, something that looks like this, right? And an Ethernet cable, you can see the plug over there, and they can be different colors and all sorts of things. Normally in a data center, they will use one color for patch panels and cabling, and another color for for different types of Ethernet that connect different things together. But Ethernet cables is the stuff that we are talking about. So a local area network, especially in the past, was all wired up. So you had a computer, and in it had a physical connection, a Ethernet card on it, and you plugged in a cable to that and to your switch, and you might have had a printer that was connected to the network. You hang that off your switch, and you might have had a couple of other devices that were connected with physical connections. For example, a CCTV camera, right? You might have had a CCTV camera in the roof above you in your office or whatever it is, and in the background, you might not have seen it, but in the background there was a Ethernet cable that was plugged into that. So that kind of defined a LAN. A wireless LAN was the same thing, except it kind of removed those cables away, right? Generally speaking, if you go to any big office today, you will see that every office has a big photocopier or printer, right? Where everybody prints their documents. So instead of having dozens of printers for everybody on their own table, only accountants nowadays, like to have their own printer on their own table to show they're really important. But otherwise, most people just use a one big printer for a whole floor. For example, at our office in Reading, that's what we have, one of these big printers. So it's spec'd really highly, and it can take a lot of stress on the network. So you could literally have 50 people sending documents over the network to be printed, and it will just receive them, queue them, and then just put them in a queue to be able to spit them out. But those types of printers, that type of device is generally, even today, still connected with a Ethernet cable. But if you look around again in the Reading office, pre-COVID, if you looked around, everybody, every salesperson, every engineer that was working there was on a laptop, and they were connected wirelessly. It's still a local area network, but instead of the cabling, it's now all about wireless technology, radio. Okay, so that's basically the difference. I know for some of you, this is like, I've heard this all before. I know, but we have an audience. I actually don't know exactly the numbers today. It might be in the hundreds, or it could be in the thousands. Not everybody knows all of this stuff. And yes, we would like everybody to have seen it, but how do I know? I don't. So I'm going to cover this. Please be patient with me as we go through this, but we want to help everybody. So those are the two major differences, and you see the difference over here. We've everything is wired, and then on the screen over here you can see we've got these wireless access points. Then in the wireless LAN, WLAN, that's how we write it, WLAN, there are terminology, there are words that we use. Like in the last episode, I used those things about optimization and governance, those long big words. So in wireless LAN, when we talk about any engineer, you're going to hear these terms, and you're going to hear them over and over again. And one of them is distribution systems. Distribution systems. If you hear people talking about LAN and WLAN, and they're talking about distribution systems, this is what they're talking about. It's the wired backbone that interconnects access points. So let me just go back one step. What is an access point? Okay, because Access point, does that mean like a door? Because the door is an access point, right? No, we're talking about wireless technology. And an access point is a device that broadcasts internet or network access wirelessly. I'm going to show you one. I have one right here. This is one of the newer ones that Extreme has launched. It's kind of really cool. This is the 305C. Really small. It fits in my hand. Nice, nice good weight, couple of connectors and stuff. And this is kind of designed to go, up onto the ceiling, onto the wall, or etc. So really nice small access point, and it's got all the new technology. But when you hear me talk about an access point, this is the type of stuff. Yours might look different, okay? Might be bigger, smaller, it might have different color. But in essence, inside here, there's electronics, there's a radio. It would, once it's connected to a cable, right, to that distribution system using a cable in the back, an Ethernet cable, it broadcasts and transmits radio waves that connect me at home to the network. Okay, so the distribution system is the wired backbone that interconnects APs. Now in your house you might just have one AP, absolutely okay, but think about a hospital, or think about a school, or think about a university campus, or that video that you saw, I think it was last week at the beginning, the MLB. You have a stadium. There's no ways you could have one access point, so you're going to have dozens, if not hundreds of access points, all right? So the distribution system is the terminology we use to describe the interconnection of all of these things. And then we talk about, you'll hear us talk about an extended server set. And this is a collection of APs, AP or APs, connected to a common wireless service. So in your house, again, if you have one, not so much, but if you have an office and you have a number of different access points, all offering connection to the same network, okay, then we call this an extended service set, set. We also talk about this, we refer to it often as an SSID. So people often talk about an extended server set identifier. That's more the techies, because that's technically the right name to call it. But generally speaking, in my conversations with friends and people in the industry, they would generally say it's an SSID, okay, a server set identifier. And that's how they kind of say, okay, what network do I connect to? So if you come to my house, if you don't know anything about Wi-Fi, you'll probably say something like, oh, what's your Wi-Fi password? What they mean when they say that is, it's what is the extended server set identifier, right? And here on the screen, you can see there is one called employee, right, for all the employees at Extreme, and there might be one called guest. So all the guests that come to the office, they want to have meetings with people over here, if they come in and they want to use wireless, we don't put them on the same wireless network as the employees because they have access to other resources. We put them on one called guest, and from that one they can get access to the internet, but they can't get access to the internal network. So generally speaking, this SSID is just a string, okay, a string of a word. Now, this is another term that, again, we use in the industry that you might not be familiar with. Like, you're talking about wireless, now you're talking about strings. What's a string? In tech talk, a string is a group of characters. We don't say words, okay? The reason we don't say words is because a group of characters might not necessarily make up a word, okay? If I say the word circumspect, it is an English word. But if I say to you C1Z question mark alpha papa underscore, do you see? It is not a word because it doesn't exist in a dictionary. It's a string. It's a collection of characters that create a string, not a word, a string. Now, your Wi-Fi SSID at home might be a word. You might have called it, Isaac's home network, or you might have called it, Isaac's guest network, something to that effect, right? That could be a string that actually is a word. But you might also have called your home wireless SSID, you might have called it, exclamation, PAP153 question mark. That would be your SSID string, okay? Is that kind of clear? I hope that's clear. I know, again, for some of you, like, oh, that's so basic. But let's not leave people behind just because we know and other people don't. Let's bring them with us. Let's help them so that people can talk the same language and understand what we're talking about. So at this very point, remember we said last week that we're going to introduce 1 minute breaks where you get up and you stretch, you turn, it's very good to do this. If you've got something like an Apple Watch or a Fitbit or something like that, and you need to walk around for a minute, this is the time. I want you to get out the chair. This is not good for us just to sit for 2 hours. No, get up the chair, stretch up, down, across, whatever. While you do that, what can you do? Watch this clip. You can stand, don't sit in the chair, get up, watch the clip if you want, if you don't want to walk around. Let's see what Rowan was able to do in 1 minute. Okay. Academy is crazy. You don't find other training places like this doing things like this, looking after people's health. Where'd you find an academy? Where'd you find online training like this? Crazy ideas, right? But it's engaging, and we love having you with us. We absolutely love having you guys with us. Hey Siri, set the timer for 20 minutes.
So, 20 minutes and counting.
Thank you, sir. So we love having you guys here. Just wanted to say it's really been fantastic. The response from last week, from our first episode was just phenomenal. It just blew away all our expectations. We got so many comments. I got so many messages on LinkedIn, and the whole team. Oh, it was absolutely fantastic. Thank you to everybody in the back office, people like John Barger, Rowan, Paul, Ben, Stuart, Claire, David. There's so many of us in the background. And also to all the people on YouTube, engineers, friends, some of you I really call my friends. I've never met you, but it feels like I've known you. We correspond, we chat regularly on LinkedIn. Friends, I'll call you friends. Thank you, friends, for helping other people that know less than you, for being, the type of community that helps, like, hey, fantastic. If you know, why not help somebody? Don't be stingy with your knowledge. Help people. It's really good. It's good. It feels good when you help others, right? Okay, so back to this training. We were speaking about this string, right? The SSID, and then this access point. Okay, here, this access point. When you switch it on, plug it in, set it up, connect it to the cloud or whatever, the way your system works. When it starts functioning, this thing broadcasts what we call beacon frames. And we're going to cover this in detail. It is so interesting. And I'm going to have a guest that's going to come on and help us to understand how this thing works. When you see it, when you understand it, it's like, oh man, I didn't know it worked like it. It's fantastic. But the short story is that access point broadcasts beacon frames, right? It's kind of sits there and it says, hey, I have a wireless network. The SSID is Isaac's home network. Hey, I have a wireless network. SSID is... And that's why when you walk around with your mobile phone in a shopping center or wherever it is, pre-COVID, maybe after COVID as well, and you take out your phone and you look at wireless networks, you see all these wireless networks popping up. Plop, 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 plop. What are they doing? Well, your mobile device is picking up these beacon frames that are being advertised by the APs, saying, hey, I'm here, I'm available. You want to use me? I'm here, I'm here, I'm here. Beacon frames. But actually how it works is really, really fascinating. So further terminology, basic server set, an AP and a collection of devices connected to the network through this AP. So if you have your tablet, if you have your mobile phone, if you have a wireless printer, perhaps you have another wireless device, maybe your TV is wireless, right? They are all connected to this access point. We call that a basic server set. Okay. The MAC address of an AP's radio is what is the BSS identifier, or BSSID, the BSS identifier. We spoke about in course 1, we spoke about MAC addresses, right? And we said every device has an IP address, but it also has a MAC address. And so a radio also has a MAC address. A radio on an access point has a MAC address, and we would call that the BSSID, the BSS identifier, okay? And every SSID is going to have that as well. So every one of those strings that you create, guest, employee, etc., that's also going to have a BSSID, a unique identifier. All right. We used the example in course 1 of an Instagram post. We said, when we were talking about, okay, we went through the OSI model and the different layers, and I kind of showed you how a packet travels from the top down and then goes across the wire and comes out the other side. And then we used the example. We said, well, if you have an Instagram post and you take a photo and you press a button, magic happens in the background, right? It's instantaneous, but in the background, your application is going to break down that photograph into little bits and pixels and give them binary equivalents, and all of that happens, and it happens in a flash of an eye. It then is going to go, from your device to your access point. From the access point, it's going to go to the gateway, and from there, it's going to go out. There's a whole lot of things that actually happen in the background. So for wireless, it's essentially the same process. It's you still have an app, on layer 1. It's still doing this. It's still being the application that you interact with, and it all goes down. The difference is at some point, where the Ethernet had the physical cable and it went out on a physical medium. The physical medium here, in this case, is radio waves. So the transport mechanism that gets you from here to the Instagram server somewhere, in the world somewhere, the mechanism is all the same. The things are the same. What's different is that transport, that wireless link between you and the access point. It might seem so trivial, right? My access point is only a meter away or 2 meters away, but it's that little bit of wireless where this magic happens, where this complexity of radio waves do their magic. And that's essentially what's different to if you send a post using an Ethernet cable or a computer connected directly to the internet. So the technologies are the same. You have 802.11 frames, right? Because 802 is the wireless. You have those frames. They connected, they transformed into Ethernet frames over the cable, right? And then they hit the switch, the router gateway, and boom, they're out onto the internet. This was, for me, the favorite slide. If you see this slide on course 1, I think it was lesson 1. This was my favorite slide. This is the one slide or the one image in my head that kind of put everything together.
why do we use zeros and ones? What is it about zeros and why do computers only use zeros and ones? Why? Because of electrical current. You have a positive and a negative. And if you can translate everything down to a 0 and a 1, you have a positive and a negative. You can put that on an electrical wire, on a cable, and you can send that down the wire. And on the other side, you just reverse the process. So computers do everything, they filter everything down to zeros and ones so that it looks something like this. If I show you here, there we have remember the binary 00011, you know, and how we make up these numbers, a bit made up of a byte made up of 8 bits. So here you can see, you know, what we have, and in this case the zeros, you know, represent that, and then the 1, it changes state. Now generally speaking, we've always drawn this as zeros down here and then a 1 up here, but what it really is just a change of state, right? So if it was up, a change of state goes down. If it was down, a change of state goes up. And so once we have zeros and ones, these are, you know, what we can put on the wire. For wireless, it is radio waves. It is radio waves. And those contain the information about a 0 and a 1. Right? Electromagnetic waves. They are imbued with data, with photons, and they carry an energy. And when they get to the other side, that is translated, reversed, and then it translates it back into 0 and 1. It's a fantastic, it's a absolutely fantastic system. We looked at something like this. And again, this type of stuff, we're going to do a section on network design, on how you design and think about wireless networks. And one of the things that we're going to be talking about is interference. The 2.4 gigahertz band, you will always hear people say, oh, that is such a busy band. There's so many devices on there, all sorts of devices. And there are, and we're going to cover this again. But there is noise that happens on that. So you never put an access point next to a microwave oven. Just don't do it. It's not good. The newer ones are better, but the older ones, not so much. Now this, for me, was an area where I really struggled when I started learning about wireless, okay? How you measure wireless. Now, just like you would measure liquids, distance, millimeters, milliliters, etc. You also have to have systems to measure Wi-Fi or to measure the radio frequency, the signal strength, right? Because think about it, a radio broadcasts, and it broadcasts at a certain strength. How do you measure it? What do you do? What is the term? What are the units that you use? You certainly don't measure it in kilos and liters. So there are measurements. Now, I looked at this, when I first looked at this, I could never understand why you would have negative numbers, right? It's like, you can't have negative milliliters, right? You can't. And you can't have negative centimeters or negative kilos. Something has a weight, right? Something has a weight. This water has a weight, and it's measured in milliliters. There's X amount of milliliters on it, but you can't get negative amount of milliliters, right? Just it doesn't quite happen. But when you measure radio, you get this term, a positive dBm, and then you get negative dBm, and it's like, oh. So if you have struggled to understand this, if you have seen this as well, and you're like, oh man, I don't get it, I'm not going to jump in now to cover this because it needs a section and it needs more time, and I'm just doing a recap. But just to let you know that this is how we measure signal power, signal strength. We do use logarithmic scales, to do this, to make it easier to understand. If you want a quick takeaway from here, this is it. If the signal is bigger than a milliwatt, it has a plus. It's a positive value. If it's less than a milliwatt, it's a negative value. What is milli? Milli is 1,000, right? Milliliter, 1,000 milliliters. So milliwatt, more positive. Less, it's negative, right? Less than a milliwatt. And believe me, there are many instances where things are less than a milliwatt. And then there's a rule, again, I'm going to cover this. If you just want one takeaway from here, that says for every 3 dBms of power, all right, gain. So think about gain as volume. If I'm listening to music and I turn up the volume, the gain, for every 3 dBm, the power is doubled, right? And the inverse is also true. For every 3 dBm of loss, the power is halved, right? So you can see on a logarithmic scale what this is going to look like, what this curve is going to look like. For every 10 dBm of gain, the power is increased by 10 times. And for every 10 dBm of loss, power is dropped by 10 times. Now, you might think that's just mathematics, but it's not. Because if you understand this, if you see this, then you know, oh, if I have an access point over here, then it must mean that if it's broadcasting full signal strength as it leaves this antenna, then as the radio, just as that wave gets further and further away, it must be dropping in power. And if you've come to that conclusion, well done. Okay, something else, couple more slides, and then we'll call it quits on this section. You're going to hear about interference quite a lot, actually. You're going to hear about interference and the different properties of radio waves. But one of the most common terms you're going to hear is people talking about signal to noise ratios, and they write it as SNR, signal to noise ratios. The best way that I can describe this is I'm in a room, my dining room, and around me there's no noise. I mean, occasionally you hear cars, go by, and you can hear probably the fan on my computer going because of the software that I'm using. So the noise level in the room is low. It's not zero, okay? If I go upstairs to my bedroom at night and I have a little tool that I can actually measure, I know that my background noise is very low at night. There's no electronics, there's no radios, there's nothing in my bedroom that's going off generating noise. But in this room there is, but it's very low. But if I brought in a radio and I started playing music over here, and if I had some friends over, they won't really fit inside it, but if I had some friends and they all started talking, they would generate background noise. Yes? And if I was recording video, talking to you, broadcasting to you, then if they were making a noise, I would need to raise my voice to be heard at the same level. For you who are listening to me to hear at the same level. Why? Because the background noise is really high. In radio, it's the same thing. If you have an access point in a room and it's the only electronic device in there, then you could say you have a very low noise level, right? It's very, very low. There's not a lot of noise happening. So your access point, when it broadcasts, it's almost using all that just to get the signal out. That's great. But what happens if there's a lot of noise? It means it becomes more difficult to hear. If there are a lot of devices causing interference, you have baby monitors and you have microwaves and you have this track and you got that, and they're all using 2.4 gigahertz, then what will happen is there's more background noise. And in wireless, remember, it's a contention-based network. So if I can't hear you properly, I'm going to say, could you repeat that again? I'm sorry, there's a lot of noise. I can't. Shh, Eric, quiet. I need to hear. What did you say again? Do you understand? That's what this concept of signal to noise ratio is. So if the radio signal is up here and the noise is here, oh, look, great, I've got a great ratio. But if this one down here, if that noise level rises, then my ratio is now smaller. And it means on my wireless, it might manifest as more retransmissions, which in end mean slower network connection. And that's generally what can happen if you're in an environment, a lot of access points, a lot of wireless devices, connection can be slower because it needs to, like, I didn't get, yeah? Signal to noise. I know I use a lot of these illustrations, but if they help for somebody to understand what we're talking about, if somebody says signal to noise ratio, oh, I know what that is. If that story has helped you, fantastic. What are the things that can cause interference, right? Microwave ovens. Not every place has a microwave oven, but those are one of the things. Bluetooth devices, that's something else. Bluetooth devices operate generally on the 2.4 radio band. So you might have, a watch that communicates over Bluetooth. You might have a Fitbit tracker. You might have a Peloton. You might have a whole lot of devices that talk using Bluetooth. Your mouse, your keyboard, right? You have a lot of these. They could cause interference. You could have a baby monitor, right? You got a bedroom upstairs, you have a baby, there's a baby monitor, there's no Ethernet cables, you use Bluetooth for that. Yeah, that could cause interference as well. One of those monitors, it could be wired or it could be wireless. Medical devices, that also operate on this frequency spectrum, on the radio spectrum. It could be 1,000 different devices, heart monitors. People walk around with heart monitors. Sportsmen often, use heart monitors and things like that. And you can watch what's happening, track their health, all sorts of things. All of these things are going to interfere, just like when you have a room full of people. Right? When you have a room full of people, you have children, you have adults, you have young people, old people, you have all sorts of people inside a room. Everybody, there's going to be interference. It's no different in radio when we talk about radio. It's the same thing. Now, attenuation is another good thing, and I'm going to show you an example of this. I've recorded a video on this. Radio waves, people say, oh, it's slow and all sorts of stuff. But if I sit inside my house, which I do, I have an access point inside here. And I have, some of you have seen on LinkedIn me building a scale models, those things over there. And I work in my garage, and it is a brick-walled garage. So the access point in here transmits, and when I stand by the access point, the signal is virtually 100%. When I go into my garage, it's not 100% anymore. Why? Because that radio signal had to travel, hit the wall, and come out the other side. There's an attenuation, there's absorption. That's radio energy, right? Traveling at almost the speed of light, virtually the speed of light. These radio waves, they hit that wall, that energy gets converted into heat, and it comes through, and there's some attenuation. There's some of that is absorbed by the wall, by the material in the wall, and so on the other side, I get a lesser of a signal, right? So that's attenuation. And we also covered this free space path loss. And what we were talking about over here is in a house, there's going to be a lot more devices, a lot more, architecture, a lot more things where the radio signal can bounce off. So your radio is really going to be limited in its range. But if you go outside, if I hang my access point outside on an open field, on a football stadium, wow, it's going to go forever. And you'd think that it would be strength forever, right? But it doesn't actually quite work like that. There is a calculation, and again, we will cover this. So even though you have nothing between an access point and a receiver, by its very nature, right? It's just physics. The radio signal loses its strength as it travels through the air. Right, free space path loss, and we're going to cover this again in more detail when we get to that, and that's also really interesting. Here you can see, if I point this out over here, right, laser, there we go. So here we have the access point, and you can see, as the distance over here increases from the access point, you see the radio signal starts losing some strength. Okay, then I hit the wall, yeah, of my garage, and you see that the signal strength drops. Yeah, just in that wall, it drops from that to there. There's this attenuation, and now I have a lesser signal, and still you can see the signal is getting less all the time. If I look at a heat map, you can find this heat map, for example, on Extreme Cloud IQ. We have a tool. It's not the best. It's just kind of to give you an idea, but there are professional tools that show you this. You can see over here free space path loss. Right here is the access point. You can see around it, nice and strong signal. As I move away, there's this free space path loss. There's this loss, a natural physical medium. So whether you are in-house or outdoors with no interference, in the air, radio loses its power. Okay, that's just normal. Now, one of the other things that we have is dynamic rate shifting, and this again is one of these things that makes perfect sense. If I'm standing right next to my access point, what do you expect? You expect that I'm going to get, the maximum rate. In this case, 54 megabit per second. This is an old access point. You can see over here that I'm going to get 54 megabit per second, right? But if the distance goes further and further away, what happens? My speed drops. Why? Because the access point is more interested in me maintaining a solid connection than only giving me, the absolutely best speed, right? What's the point of saying I have great speed, I'm able to talk, incredibly fast, but if I have to ask you to repeat that over and over and over again, it doesn't make any point at all. So wireless devices, generally, they decrease the data rate with distance to avoid retransmissions. And so that's why we see things like this. My access point is, it's capable of 1750 megabits per second. Well, the total capacity is 1700. Advertisers are clever. The total capacity is that, but that's made up of, so much on the 2.4 and then so much on the 5 gigahertz. So now it's not so much a 1750 megabit per second, right? And then these things change. There's a lot of overhead in wireless as well, because of these retransmissions, and that takes up 50 to 75%. About 50 to 25% of overhead. So you never get 100% throughput. So you end up with something like that, which is still, absolutely fantastic. We've looked at access points, and we've looked at the wireless LANs. And if you have a network properly set up, then if you have various access points, you can roam from one to the other. You don't have to sign out, sign in at another one. It's magic. It kind of just happens in the background. So we've now got to the end of this section. We're going to have our 10-minute break right now. And then when we come back, I have a chat that I'm going to be talking about. I'll see you after this break.
Progress is an action. It's movement that pushes us forward, driving us to a better destination. And it's rarely achieved alone. At Extreme, we believe the progress is sparked by connecting our customers, not just to the internet, but to the world, to each other, effortlessly. Because we believe that when we connect, we learn, we create, and we grow together. We also know that progress is about leadership and innovation, about being on the cutting edge, whether it's inventing the first gigabit Ethernet switch or delivering the first and only cloud-driven end-to-end enterprise networking solution. It's being one step ahead and always looking forward, advancing, unafraid to try something never done before. We won't rest until we make every network experience truly effortless. That's why we push the boundaries of technology, leveraging the powers of machine learning, artificial intelligence, analytics, and automation. Progress is driven by people, our people, who deliver continuous innovation at cloud speed. Because we know that's how our customers need us to be. We see a world where enterprise networking is autonomous and effortless, advancing the way we connect, work, and live like never before. Progress is action. It's movement. And we want to take you on that journey forward.
Okay, welcome back, everyone. So this section is going to be the start of the technical section. So all the techies are there like waiting. I've had a lot of trouble with this section. I'll tell you what that trouble has been about. When I teach, I like to make things really simple for people to understand stuff, and I hope that I do. It's not always successful, but I really try. And I think the biggest reason for that is because I'm a very visual learner. So sometimes if I need to learn something, I'll read it. Some people will read something once and they'll instantly get it. I mean, they're just blessed in that way. I have to read something 7 times, 8 times, right? Sometimes I have to slow down my reading and literally go word by word. And then, my mind then starts firing off these electrons. I start asking myself questions about each word. And so I take longer to learn, I think, than most people. So books take me longer to read, things take me longer to understand. But something that helps me a lot is when I can see in my mind when I can see what we're trying to understand, what we're trying to look at, right? When I can see it, when I have a picture of it, I call it like I need a hook to be able to understand things. And if I can see that hook, then I can relate to that. And for me, that hook is about stories, analogies, examples, things that I can relate to. And when I've taught around the world, many of you who are watching, or some of you are watching this, but many of my pupils from places I've traveled to around the world, this is a technique that I used because it helped me to understand. And so I would tell stories and I would tell these things to help people to see. And some people would get totally bored, right? Because they are those people that understand everything, but you can't always make that assumption that everybody understands. And on a course like this, we really can't make that assumption. So why I was having trouble with this is everything that wireless is about starts with the basic concept of a radio wave, right? So I go to bed thinking, how am I going to explain a radio wave? And then my mind starts going and I wake up at 2 o'clock in the morning and there's one question stuck in my mind. And that question is, why do you call it a radio wave? Why don't you call it a radio square or a radio triangle or a radio loop-the-loop or diddly-dosh mongy? Why do we call it a radio wave? Do we just assume? If someone said to me, why do you call it a radio wave? What would you answer? So these are the questions that go through my mind at 2 o'clock in the morning. And I've been struggling with, how do I explain this to people? How do I get people to see a radio wave? Because what does a radio wave look like? Have you ever seen a wave? I mean, We know we get satellite signals from space for our GPS. We know that. Have you ever seen a wave? I have a satellite dish outside somewhere to receive my television signal. Have I ever seen a radio wave? So, if we see, it's easier for us to understand. Yeah? If you think about medical research, bacteria, until we could see bacteria, we knew there was something that was killing people, but it was only when we were able to see it that we started to unravel it, to understand it. When we started to see atoms, we started to understand that this is the way they work. They rotate, they spin at this rate, they spin at, when we saw, people, like, oh, the world is flat and blah, 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 blah. But when you see the photo of the Earth, there can't be any doubt, right? I mean, scientists do this. They know how to do it. I'm not a scientist. I don't have access to that lab equipment. So last Sunday, I drove to a lake quite close to my house. We're allowed to, to drive out. We can go to parks. We're now coming out of lockdown gradually in the UK. So I drove to a park, and of course you have to wear a mask, especially if you're around people. So all of this that you see is all according by the book. But I had an idea how I would show you what a radio wave looks like and why we call it a wave. So I recorded this on video. Please stay tuned. So I came out to this beautiful little lake by my house. You can see it's a beautiful sunny day in Cambridge, and I came out here to find a way to show you what waves are, because essentially radio waves are invisible. So I came out, picked up an old piece of wood and threw it into the lake, and you can see as it hits the water, you can see those concentric circles of energy going out from the center. So let's move over to the whiteboard and I'll diagram those for you so we can understand what they look like. Interesting, right? Because I'm going to show you on my tablet, I'm going to draw this out. But you saw what happened over there. When I threw that log in the water, you saw what happened. There were concentric circles, right? These concentric circles of energy, right? That moved out evenly from where that drop created that burst of energy, from where that log created that burst of energy. If I had dropped something a lot bigger, I would have had the same effect. If it was a lot heavier, what would have happened? Well, imagine if I had dropped a 500 kilo steel ball onto that lake, into that area. Well, what would have happened? You would still have had concentric circles of energy moving out, radiating out to, across that whole lake, right? What would be the difference? Well, where the ball fell, it would have generated a much bigger wave. But the end result would have been exactly the same. So let me now draw on the tablet. I'm going to just focus completely on here. I'm going to draw on this tablet, and I'm going to show you how we call it, why we call it a wave. Why don't we call it just a splash? Why don't we call it, a radio, square? Why do we call it a wave? So stay with me. for these next few minutes as I illustrate over there. You might see me looking down, but you know exactly what it's about. So let's imagine that this white line on screen is the actual surface of the water, perfectly smooth, no ripples, no wind, no nothing. Okay, and here comes the log, and the log gets thrown into the water and it hits the water. What happens when it hits the water? Well, immediately waves are going out right from the center. Now what I'm going to do over here is I'm going to stick a big fat piece of paper over here, right? Because I want to map what is actually happening, the shape of a wave. So what happens? What happens when this wave over here hits the water? Let's call this time, right? That's time. Right. So when the wave eventually hits over here, what's going to happen? Well, it's going to push the water, right? It's going to push the water. So as it hits the paper, that very first dot is going to be created, then another dot. So let's say these are all hundredths of a second, right? Hundredths of a second. As the water pushes through, right, that which is the peak is now moving in that direction. So all of this stuff is moving, and I'm plotting it every 100th of a second. Now, once it's gone past, of course, it carries a wake. Yeah, it carries a wake in the back, and that wake is going to follow. I'm plotting it all the time. Now look what happens if I go in and I join that. It's a little bit difficult to draw, but look what happens. Yes, it starts to look like a wave. A wave, one of these things. It starts to look like a wave. Now, what will the next one look like? Well, the next one, we know that energy, as it travels, be it in the water or a radio wave, as it travels, it loses energy. So the second wave, or the next wave that comes in, actually, it's not in front. If this being the first one, the second one would be here. So let's have another piece of paper over here. The second one, the wave would start, but you see what happens? The amplitude, oops, that's bad. The amplitude would be less than this one. Here, the amplitude is much more. Why? Because it has more power, right? It has more power. And as further and further waves leave that center spot outwards, they have less and less power. So the height, the amplitude of that wave is less and less reduced. So the first one really big, next one less, next one less, next one less, next one less, until it's not even a wave, it's a ripple. But if we were to draw it, it would look like that. And that's why we say that this is a radio wave, because we've measured the same thing on an oscilloscope, right? So if you look at the oscilloscope, which is designed not to look at water waves but to look at electronic waves, that's what we will see on an oscilloscope. So I hope that that's been really clear and helped you to see that all around you, every day, all the time, you are surrounded by waves. As you talk, there are waves of energy carrying your voice. You're listening to people around you talk. You are hearing waves of energy. In this case, because it's in our frequency range, our ears, we translate that into pitch. Our minds convert that into words, and we can understand what he's saying. So, easy explanation. I hope that that's been clear. I hope that's now become interesting. Because now you should start to see, when we talk about radio, you should start to see why we talk about a radio wave, right? This was a wave of energy. That wasn't it wasn't a radio wave. It was just a wave of energy. But you have waves that produce audio. Our ears are tuned. They are antennas, and they can hear radio waves. A child can hear from about about 60 hertz to 20,000 hertz. They can hear that entire range, right? Young people like me, not so much. I can probably hear, 300 hertz till about 15,000 hertz. That's about my range. But that's just hertz, 20,000 hertz, 20,000 hertz. What's a hertz? 1 per second, So 20,000, 20,000 per second of these waves in 1 second. So that's the range that I have. But wireless access points also have a range that they listen to. They're certainly not listening for audio waves. You can play a radio in front of an access point. The access point doesn't know what to do. It can't interpret that. It means nothing. An access point has a particular range of frequencies on which it is tuned to listen in. Very, very sensitive. Okay, all access points, they have this sensitivity to listen for these specific radio waves. So if we understand now what a radio wave is and the shape of a radio wave, okay, which we can get from, for example, just from this drawing that I made, or tools in the laboratory, you can look at an oscilloscope and you can see that same thing. If you can see that in your mind, then you should start making sense of some of these things that I'm going to be talking about, because a lot of technology that we have today is modeled, and I've said this a number of times, on human communication. I am an access point. And you watching this, you are an access point. We're saying, this guy's lost his marbles. No. I have a transmitter, and I have 2 antennas, not one. I have 2 antennas. And 2 antennas gives me the range so that I can hear someone behind me, to the side of me, here, in front of me, and on this side, the same thing, right? If I lose hearing in the one ear, I still have hearing. I still have periphery hearing. Perhaps not as good as 2, but I can still hear. So I, as a human being, have 2 antennas, right? And a transmitter. If you stand with me, now that some of these restrictions have been lifted in the UK, we can go out, like to the park, 2 people, and we can have a chat. So if you were to come with me and we go to the park and we take a walk, and you're 1 meter or 2 meters away from me, and I'm chatting to you. As I chat, I'm transmitting radio waves. Okay, it's audio. Your brain interprets it because of the frequency that I'm talking at. It comes out as audio waves, but you interpret that and you can hear me speaking. If you walk 10 meters away from me and I speak at the same volume that I'm speaking now, you will hear me, but you will struggle to hear me. If the signal to noise ratio is bad, in other words, if there's a lot of background noise, you won't hear me. And you will need to come closer, or I will need to talk with increased power levels. Yes. Or you will have to say, could you repeat that? I didn't hear you again. I didn't hear you again. All of us are familiar with this. When we're on a mobile phone talking to somebody, right? I know most of us text nowadays, but when we're on a mobile phone, we have a conversation, and you often hear as part of the conversation, sorry, I can't hear you. Are you moving? Can you just stop moving? Can you just stop moving? I can't. Hello? Yeah. That's familiar to all of you, right? All of us know that story. All of us have been there. So when I say we are an access point, that's what we are. When we talk, we transmit audio waves, but let's call them radio waves, in a spectrum that other people can hear. Your dog can hear a lot further. So in that same example, if I went with a dog, right, and I got the dog to do things and gave the dog commands, if the dog was close to me, he would hear me. But if he was 10 meters away, where the human might not hear me, the dog would still hear me. And maybe 20 or 50 meters away, the dog would still hear me. Why? Because they have much more sensitive hearing. Their antennas are much better, are much more sensitive than what a human is. They also have 2 antennas, right? That's what they do. So if you can now see in your mind a wave, a radio wave, what it looks like, and now you start to see that as humans, when we communicate, we are just using the principles in nature, and wireless and networking and all of those are using those same principles. If I'm in a crowd, I have to talk louder for people to hear me. A wireless access point placed in a room where there's a lot of different devices is going to struggle, right? Because everybody wants time on the access point. Everybody wants to get through, but there's a lot of noise. So what do engineers like me who knew nothing about wireless do? People say, oh, well, this wireless access point is so slow. I went in and I would look at the settings on the access point. Oh, look, there's a setting here. Here's the problem. This is only broadcasting at 12 dBm, of power. Let me slide it to them. How much does it go? Oh, it only goes to 20. I wish I could buy an access point that's got 100 or 200. But this is rubbish. It only goes to 20. And I'll slide it to 20. Boom. Now what's happening? That access point is super sensitive, right? Super strong. And it might work if all I have is one access point. But if I have a room and now I put in 4 or 5 access points, and now they are all shouting at full volume, always advertising, hey, I'm so. What happens? They kill the network because they are now they're not just saying, hey, I'm this, here's my beacon identity. I am Isaac's home network. I am Isaac's home. Now they're saying, I am Isaac's home network. And that other guy saying, I am Tony's home network. And everybody is shouting. Efficiency drops, and you think this is rubbish equipment. This is all rubbish because look at this. I've set it all to maximum, and now it's not working properly. The opposite is true. Drop the power, right? If you think about this in a family way, when I lived in South Africa at Christmas, all my family would come to my mom's house. Cousins, nephews, aunts, all of them, and we'd just eat and feast and then eat some more, right? And when we were all in this big double garage eating away, all of us would be talking, right? And we'd all be shouting, Mom, pass that. Oh, Mom, can you give me some change? Everybody would be shouting. The little kids didn't have much of a chance, right? Because if they didn't raise their voices, they couldn't go above the noise. It's the same issue with wireless access points. It's the same issue with the way we communicate. It's the same issue with radio. So start to see, as I talk about radio, as I talk about these things, start to see these things in your mind, right? When I talk about attenuation, when I talk about free space path loss, when I talk about, that sound can be absorbed, radio waves can be absorbed and they lose energy when they go through a wall. If you sit inside a closed room and you talk, you can hear yourself really well because your antennas are right there. But if the door is open, then you talk, they can hear you talk. If you close your door, what happens? Your sound, those sound waves, they are absorbed by the door, by the closed door. They still get through, but the volume is decreased. Remember that attenuation that I showed you? It now goes down. They still hear me, but it's less. They might hear me well enough. If the signal to noise ratio is low, they might hear me well enough to be able to understand what I'm saying. But if the background noise, if there's an ambulance going past or a loud motorbike going past, they might need to ask, hey, what did you say? Can you just repeat that again? So I hope now that I've spoken about this and helped you to see radio waves, that now as we start looking at the technicalities, as we start looking at terms and discussing terms like amplitude and wavelength, I hope now that as we go into this, that you have a much better idea of what's going on when we're talking about radio waves, right? Human, I'm a human, but I'm an access point. I have antennas, I have a transmitter. This, if I vary this, more people can hear. If I increase the level, people can hear, and they can hear further away. If I decrease this, then this is what happens. If I shout too loud, no, right? So it's that time. 1 minute. What can you do in 1 minute? 1 minute. Get up off your chairs, stretch up, down. Come on, just for 1 minute. The timer will come onto the screen. Go for it. See you on the other side of this. What can you do in a minute? Oh, that guy's crazy. Yeah, let's get into serious things. This is the part techies love, and some might fear, but never fear. This is gonna be really good. Let's look at the agenda. So I have decided I'm not going to do this part and that part. So when I say I'm not going to do it, what I mean is I'm not going to do it. I'm not going to do it now. These subjects, they need a little bit more attention, and I want to bring in one of our experts to spend more time on this, because this can be really, really complex, and to hit you with that right up front when we're starting to get into the technical aspects, I think is a little bit unfair. So I will cover this for sure. This will be covered and in detail, but just not now. So as always, let's look at the objectives. We're going to explain the radio frequency signal. We're going to look at effects of on radio signals. Signal to noise ratio, which we've kind of already touched on. I don't think we're going to do much more about that. And then antennas as well. So we'll start to get into antennas. All right. So let's get down to basics. And let me just bring up my pen over here so that I can draw over here. We've seen from the illustration that I made earlier when I went to the lake and threw that log in there, how we got to the fact that a wave looks in this manner. Now remember, waves, you have audio, radio, and if the frequencies just keep going up, we have light waves, and they all carry similar characteristics. They all have similar characteristics. For example, radio waves and light, well, radio waves move at the speed of light, travel at the speed of light. And on Earth, they travel almost at the speed of light, but we know for sure that in a vacuum, they travel at the speed of light. So if you think about that, when we say radio waves travel at the speed of light, maybe you've never considered that, but when you're talking to somebody, with a mobile phone, or even if you think about the rover that NASA sent out to Mars, and that's sending back images. I think they said the other day that it takes about 20 minutes for a radio signal that's sent from Mars to get to here. That's 20 minutes when it's traveling at the speed of light. That's pretty amazing, isn't it? 20 minutes traveling at the speed of light. That's far away. So a lot of these things have very similar characteristics. But if we were looking at waves, then you can see that we talk about a concept like wavelength, right? Wavelength, that concept over there. And what is wavelength? Well, wavelength is from one point in a wave to the exact same point on a sister wave, right? They look in exactly the same. In this particular case, these are, this is exactly the same wave being repeated. Could be a particular frequency. And so this here is the wavelength, and it could be any point, right? You could go from here to here, and that would be the wavelength. The next thing that we want to understand about waves, so this is terminology really when we're talking about waves. When you're talking to somebody about radio waves, this is the type of stuff that you would use, the language that you would use. This over here, of course, to there, yeah, that's the amplitude, amplifier, right? If we're talking about a hi-fi, an audio amplifier, what does it do? It amplifies the signal. That translates to you saying, oh, that's loud. The music has gotten really loud. If you go to a rock concert, when lockdown ends and we all go to rock concerts, you'll see they have massive banks of speakers in the front, right? And it's really loud. If you're anywhere close to the front, it's incredibly loud. But if you, sitting right at the back, half a kilometer away or whatever it is, 100 meters away perhaps, the sound is not as loud. Why? Because we've already seen that as radio waves travel, they lose energy. So they then put more speakers, 50 meters back or whatever, so that everybody can get the same experience. If they want to make it louder, someone goes and turns up a knob or raises a slider and turns up the gain, right? That's the amplification. We hear it as amplification, as it getting louder. So this is the amplification of this particular wave. This here, the one oscillation, is how many times this wave goes past a particular point in 1 second, right? So we call that Hertz after the German scientist Hertz. And so how many of these waves come past this particular point in 1 second? So if that was a point, well, this would be 1 second, so one wave comes, that would be 1 hertz. So amplification, oscillation, and wavelength. These are very important terms to know. Now, these radio waves are waves of energy, and they carry our data. Our data is sitting on top of these particular waves and of energy, and as they travel, they carry our data, right? So they leave the transmitter, they have been energized, they leave the transmitter. When they get to the antenna on the receiving device, it demodulates that, it interprets what it's received, converts that back to zeros and ones, right? So it's radio waves carrying our data, our zeros and ones, in represented or in terms of electrical charge, right? Like when we put it on the wire, the positive and the negative, it flows down that Ethernet cable. So these are the terms that we talk about. Now let's move to this one over here. Here you can see, of course, this wave, right? To there, that has a large amplitude, or a larger amplitude than when it connects to that, when compared to that particular wave over there, right? Not all waves have a continual pattern, right? A pure note. If you hit a note with one of these tuning forks, if you hit a tuning fork, it will emit a specific note at a specific frequency, and that will be a pure sine wave. But radio waves don't generally travel in pure sine waves. They all over the place. So here you can see different amplitudes of waves. Small amplitude over there. And this is what we spoke about when I spoke about frequency, right? Frequency, oscillation, how many times per second. If this was 1 second, then you could see 1, 2, 3, 4, 5, 6, 7, 8. 8 hertz. 8 times. This wave is coming past a particular point 8 times within 1 second. So this would be termed high frequency, and that over there would be termed low frequency. Why? Because over that same point in time, it might only have 2 waves, 2 complete waves that might go through. Or in this case, starts here, so that will be 1, 2. Yeah, about 2 complete waves. So these are really important terms to understand and get this. Now, this is an entire subject on its own. There are people, I used to know people in South Africa that their entire career was all about designing waves. And so you can literally spend your entire life knowing, understanding, and studying waves and the behavior of waves. This is such a big area of knowledge. So don't think that, Isaac has now showed me everything that I need to know about radio waves. That's that's not the case at all. There's a lot more to learn. So I do encourage you, and I have encouraged you on course 1, go to YouTube, go. There's so many good videos talking about waves, radio waves. Go read them for your interest, for curiosity. It's fantastic to learn about this stuff. Really, really interesting, right? The higher the frequency, the shorter the wavelength. Okay, the higher the frequency, the more of these, the shorter the wavelength. That's natural, right? If you're going to have many more within a second, well, the wavelength has to be shorter. That's logical. And the inverse is also verse is also true. Right. Let's now look at another term that you're going to use, which is phase. People talk about phase. What do they mean by phase? Well, take a look at this on your screen at the moment, right? It's a pure sine wave. Pure, it's a single frequency just vibrating away beautifully, and we've looked at this on the oscilloscope or whatever it is, and there it is. A lovely thing. Now, we can label these, we can draw this based on degrees, right? 0 degree is, well, it's over there. When it reaches maximum 90, that's 180, and and off we go. Same thing starts over and over and over again. When we want to look at it that way, phase. Now look what happens when you have another wave, all right, that joins this. Oops, how did that get there? Look at that. What's happening over here? Here, this we say is out of phase. There are 2 waves. So this was the original wave over here, and then I have another wave, but going in the opposite direction, right? Still the same amplitude, still the same amount of hertz, but it is out of phase. It's not perfectly. If it was perfectly in phase, then what you see on the screen over there you would actually just see it as one wave, and it might be many of them layered on top of each other, but it would appear as one because they are perfectly in phase. So this is an important concept for you to know, that this phase thing, where waves are slightly out of phase, and this is not a bad thing at all. Certainly not for radio. For audio, that might be a different issue altogether. Some more terms. You already heard me mention this, which was gain. When I was talking about amplitude, I said, you go to the amplifier, you turn up the amplifier, turn up the volume. Yes, you turn up the gain, right? You can think of gain as somebody shouting, raising their voice. You lift up the gain. What am I doing? I'm raising my voice. I'm lifting up the gain, the amplification of that signal. Gain is the positive difference between two amplitudes, right? So if you have amplitude A and amplitude B, and B is higher than A, then the gain is the difference between those two. So this was at 100, that's at 120. The gain is 20. Yes, the gain is 20. It went higher. That should make sense. Now, amplification of a signal results in gain. We know that you make it louder, you get this gain. Gain is a measure of amplification and is measured in dB, in decibels. That's the terminology that we use. It can occur naturally. Okay, it can be completely intentional from an external power, like an amplifier. So if you wanted to amplify it, you could do it that way. But it's not always intention. It can occur unintentionally as well. This gain that we're talking about now, not so much with an audio signal. That's not really easy. If you wanted to, you'd have to turn up to see. But in radio waves, because radio can bounce off objects, it could cause that one wave bounces off and then amplifies the original wave, in giving you an extra gain, giving you further gain. So gain could be intentional or unintentional. And on the other side, you also have loss, which is the negative difference in amplitude. So the other one was gain was the positive difference when it was base was say 100 and now it's 120, and now base is 100 and this is 80. It's a loss. Yes, a loss. That's what we talk about it. And that can be caused by things like attenuation, a reduction or loss of the signal strength. We know this already from free space path loss. We know that if we just put an antenna in and we broadcast a radio signal with distance, just because of physics, it's going to lose its power. But if it travels through mediums, right, a brick wall or whatever it could be, it might also lose it, and that might be unintentional, right? Unintentional. That could just happen. Other characteristics that we find within radio waves are reflection and refraction, and we'll look at those. So let's look first at reflection over here. So we have a radio frequency signal coming in, and it hits a particular medium, whatever this could be. It could be a steel wall. It might be glass, very thick glass. I don't know. So if it comes in and it bounces, if it's reflected, it will be reflected off, especially if it's a smooth surface, it will be reflected at the same angle that it came in at, right? And that could be buildings, for example, cars, flat stretches of ground, and bodies of water, for example. Each time the signal is reflected, what happens? The amplitude is reduced. Think about amplitude, right? The height, if you want to call it the height of the wave. Each time it bounces off something, that amplitude is reduced. Why? Because it's traveling almost at the speed of light. And when it hits a surface, there's going to be a certain amount of energy that's going to be transferred into heat, and then it's going to be reflected off. And when that equation happens, it loses. So the amplitude is going to be reduced, meaning the power of the wave is going to be reduced as it bounces around. Yes? Okay. And this reduction, of course, also depends on the material, right? So some materials, the reduction is going to be less than others. Some material, when the radio wave hits, it will be, it will reflect, but it will drop a lot of energy at that point in time, and others won't. So just because it reflects off something, it doesn't mean that every surface will have, the same amount of energy absorbed, and hence the amplification will always drop by the same amount. No, it's dependent on the material. So we have reflection, and then we have refraction, right? Refraction. So that's when you sometimes see refraction with light. If you take a pen like this and you put it in a glass of water, you will see that the part that's under the glass, that's in the water, kind of, it feels like somebody bent that pen, like somebody bent that object. Why? Because it is refracted, right? So with radio waves, the same thing happens as well. So it's a change of direction. So the radio wave is coming in, it hits a particular material, and it changes direction due to the changes due to the medium, right? The signal may also be partially reflected in that particular equation. So we have reflection of radio waves and refraction of radio waves. Remember, radio waves are physics. They are limited to the laws of physics. Now, why is this kind of important to know? Because in lesson 1, we spoke about one of the topics that we're going to be doing, that we're going to be covering, is about designing networks, right? It's about designing robust and scalable wireless networks. And if you as an engineer are going to be designing or thinking about, or maybe not even an engineer, maybe you just run your own business and the customer has asked you to go install some wireless and you thought, oh, I'm going to attend this course to learn all about this. You have to think about it. It's not just about, oh, let me go buy an access point. This one looks good. I'll go and buy that access point. You have to think and consider where you're going to put this access point. What is the environment like? Is it a warehouse, full of metal shelves? If that's the case, then these elements are going to come into play. Because if you just decide, well, I'll just put one access point on here and everything is going to be okay. Maybe not, right? Because there's going to be a lot of reflection, right? That might help you, but it could also dramatically hinder you. Or you're going to get refraction. Now, how will that help you? Is it good or bad? These are elements that you have to consider when you start thinking about wireless, when you start thinking about deployments, when you start thinking about, oh, which access point let's put this all in and we'll just go chuck it in. And because it worked in that building, use the same technology and just put it into that, to another building. No. In the UK, I live in the UK, so I can speak for, a little bit about the UK, and I've been to America as well. But in the UK, you can go to places like cathedrals. I think it was a couple of days ago, I went to a cathedral in a town called Ely, in a city called Ely. And the walls, they are absolutely hugely thick, made of concrete or solid, solid material, brick material that, they made in the 13, 14, 1500s, 500 years ago, massive thick walls. If you're going to have radio signals in there, you can't just take the approach, oh no, we're experts in wireless, we've put dozens of wireless, access points in a school, we know how to do this, no problem, we'll just go it up and just. It's not like that. You have to think about these things. These are topics that you have to consider, because these are characteristics of radio waves. So we've spoken about reflection, refraction. Another one is scattering, right? So it's like reflection, but the surface in this case is not smooth. It is uneven. Okay. Again, it could be a brick wall, a rough concrete wall, decorated wall, for example. And in this case, when the radio signal hits, it doesn't just reflect off at the same angle. It could be scattered, completely scattered in all directions. Years ago, people would see this as a terrible thing for Wi-Fi, but from 802.11n, radios were able to actually build on, say, no, this scattering of signals is actually not a bad thing at all, because it pushes the signal in multiple locations, and then the antenna, if you have 2 or 3 antennas on the access point, they can detect the strongest one and use the strongest one that comes off it. So radio wave characteristic, the scattering, right? Again, think about it with light. If you stand in front of a mirror and the mirror is a perfect mirror, you see a perfect image of yourself. But if the surface of the mirror is not perfectly smooth, if it has concave and convex, what do you see? Well, it's what you see when you go to a circus and you walk in and there's a slightly convex mirror or a concave mirror, and makes you look incredibly fat or incredibly thin or incredibly weird, right? This is what we're talking about here. Just like light can be scattered, radio waves can be scattered as well. What about absorption, right? Absorption. The same thing. Some materials will absorb radio waves. Yes, you can do this. There are rooms, there are occasions, security, high security, military, where they have materials, on the walls that absorb radio signals, right? That don't let anything, go out from that, room, etc., etc. So materials can also have higher or lower absorption rates. So the signal comes in at a particular strength, it doesn't bounce off, it might get slightly refracted, but it comes in and it then it loses energy as it comes in because it's absorbed by the material, right? Now, one of these materials that absorbs energy is water. Water absorbs it a lot. And guess what is one of the most common things on planet Earth that is made up of a ton of water? You are made up of almost entirely made up of water. So you might be the reason you got bad Wi-Fi signal in your house. Unfortunately, there's nothing much that you can do that, right? Because you're made up of water, so it absorbs a lot of that. So let's look at some of these. Over here. These materials, right? So gas. What about gas? Well, what's the severity? Very low. Minimal. An example. Air, for example. So radio waves in air, they travel almost at the speed of light, that would do that in a vacuum, so no big deal. What about wood? Well, it has a low severity partition wall. Same thing for plasterboard, okay? What about glass? Ooh, glass, right? So glass, also low, and you can think of windows. In my lounge where I've got my access point, I have a glass door that kind of opens out, and whether I open the door or don't open the door, when I sit in the garage doing my scale modeling, the signal is still weak. If I open it, it doesn't particularly get stronger if I open the doors. Why? Because radio can travel right through, so it has a low barrier. Water, you and me, medium, right? Damp wood, aquarium, those types of things. What about bricks? Also medium, inner and outer walls. Marble, medium, inner walls, for example. Paper rolls. Wow, did you know that? Paper rolls, the absorption is high. Mass-produced paper. So here's an interesting one. If you asked to go and install wireless access points at a paper mill or at a newspaper where they receive these massive big rolls of paper, you would have to consider that and take into account the fact that paper rolls massively absorb are massive barriers for radio waves, right? So you would have to think about that and do some calculations and figure out, we can't just put one access point in this warehouse full of paper. That's not going to work. We have to think about it because of the medium. The radio waves are going to be absorbed by this. So paper rolls, very high. Concrete, high. Metal, foil, high. You see how these things are going to impact on how you think about wireless networks, on how you think about implementation. This is the point of this course. We teach you the technical, but we also give you more skills, things for you to think about to make you brilliant at what you do. We're going to need to land. We're going to need to land on here. So I think what I'll do is I'm going to finish here, and then from next week. So I'll make a note. Finish So lesson 2. So we'll finish here in lesson 2, and then next week we'll carry on from here, where we start to look at antennas. This is quite an interesting part, where we look at antennas. We look at the term isotropic antenna. So that's going to be something that I want you to do some homework on. What is an isotropic antenna? Go into Google, go into whatever search engine that you have, go and do a search for isotropic. Okay, go and do a search for antenna signals, and you can also go to Extreme and do a search on Extreme documentation for antenna patterns, and we will carry on from here next week. So next week we'll pick up from here and off we go. We start talking about antennas. So thank you for joining me. Thank you for being part of Academy lesson number 2. We've got another 6 lessons to go. We've made some good progress today. We've learned quite a lot about radio, hopefully seen a couple of pictures in our head about radio, seen the little clip. Thank you for being with us. Appreciate your time. I know your time is valuable. If you're watching after the event, if you're watching on demand, please feel free, put on YouTube, there's the comment section. If you have questions for us, put the question over there. If you have comments, if you want to give us a thumbs up, please do so. Feel welcome. If you want to talk about this on LinkedIn, hey, fantastic. Go and do that. I'll comment on there. I'll respond back to you. Thank you for watching. Thank you for being with me. I'll see you next week. Same time, same place. Cheers.